All right, welcome back guys to another video. In this video, we're gonna start covering the Euler method. You'll see that the Euler method is pretty straightforward, it's pretty easy. There's really nothing too difficult about it. All we're doing in this chapter, it's we're trying to basically solve a differential equation by approximating it numerically. Right, in the previous chapters, just like we did in chapter 5, we cover right to the power series for the Frobenius method. Right, we're trying to approximate it using a series, but this one we're trying to approximate it using a numerical methods. In this case, it's the Euler. So an example that we have here, we have y prime is equals to y. We have an initial condition where y of 0 equals 1. And we have h, which is our step size of 0.01. You can see the formulas that we have here for every x that we get. X of n plus 1, we have that is the previous x plus a step size. And then for the y, it's the previous y plus the step size times the function of the previous x and y. So let's do a quick example so you guys can see how this one works. So basically from our initial conditions, right, we have a y of 0 equals 1. We can get that the x of 0, right, the first one right at the beginning, it's 0, right, because that's our value inside the parentheses in the y. So x of 0 is 0. And therefore, we have that y of 0 will be equals to 1, right? That's just our initial conditions. So we put that as a coordinate form, and we're going to get that x of 0 and y of 0 is equals to 0, 1, right? So this is just from our initial conditions. So now, starting with these values, we're going to use the formulas that we see over there in the box so we can get our first step. So in step 1, for x1, using the formula, it's equals to x0 plus h, which if it's then 0 plus 0.01, which equals to just 0.01, right? Finding the x is pretty straightforward in any method. We're just moving that much amount in the x direction. For the y1, you can see using the formula, we're going to get that y1, it's equals to y0 plus h times f of x0, y0. And then that function, that f of x naught, y naught, we're going to change that to basically the equation that we have. And you can see from over here at the top, we have that y prime is equals to f of xy. So if we have here, then f of x0, y0, that just equals to our y prime in that evaluated in that step. We'll do more examples, so hopefully this becomes clear, but at least for now, you just know that our function, in this case, our function fxy is just y. Therefore, our formula here, we have y naught plus h times y naught, which is just equals to 1 plus 0.01 times 1, which it's just 1.01. So when you put this in coordinate form, x1 and y1 is just 0.01 and 1.01. You can see it's pretty straightforward, it's pretty easy. It's not difficult at all. And we just continue repeating the steps, until we want to stop. So all of this is just basically approximating our function. All right, so let's continue. Let's do another step. So in steps 2, we're gonna find x2, and you can see we just plug in the numbers. It will just be x1 plus the step size. So it's 0.01 plus 0.01, which is equals to 0.02. And then for y2, you can see already simplifying that it is y1 plus h times y1. So it will be 1.01 plus 0.01, the step size, right, times 1.01. And when you multiply all of these numbers, you end up with 1.0201. And writing this in coordinate form, we get x2, y2 equals to 0.02, comma 1.0201. All right, let's do one more step. So step 3, we are looking for x3, right? So x3 is 0.02 plus 0.01, right? And this is equal to 0.03. So I think you guys already get what's going on in the x. And then for y3, we have that it is equal to y2 plus h times y2. So you can see the pattern, right? The new y, it's a function of the old one. So plug it in here, we get 1.0201 plus 0.01 times 1.0201. And when you multiply and add up these numbers, you get 1.030301. And once again, putting them in coordinate form, x3, y3, you get 0.03, comma 1.030301. In this case, I'm not truncating some of these numbers. I know that they're kind of long, but just since we're dealing with numbers that are really small, I just want to keep them as close as possible, as accurate as possible, to not, increase my error in this problem. So you can see that if we were to solve this equation, y prime equals to y, right? If you use the separation of variables, you will basically find out that the answer is equal to y is equals to e to the x, right? If you were to solve this, analytically. So basically, we were trying to approximate this function, and you can see we are on the really, really small end because our h size is so small. So we're gonna take a lot of steps basically to approximate our function if you want to like go and from like, let's say 0 to 1 or something, right? So depending on your step size, that's how accurate you're gonna be. The smaller the step size, the more accurate you are, the closer you are to actually basically approximating your function. And we can find the error based on our h size. So our global error is just the h. So you can see our error overall, it's how far we're gonna be away from our actual solution. So if you were to multiply this times 100, we are about 1% off overall. But our local error is h squared. So for every single value, we are just 0.0001 away, or the 100 will be just like 0.1% off for every value. So once again, if you were to plug this in a calculator, e to the x, and you were to plug in for x, when it's x is equals to 0.01, your y, you should have about 1 point something, 1.01 something, right? Plug in that x into the e to the x, and your y should be a similar value. So once again, we are about 1% off. So if we were to increase our step size, of course, we will even getting a greater error. Right. So this is the first example of the Euler method. Let's do another problem so you guys hopefully can get the logic of this. All right. So in this problem, we have the function that we have is that y prime is equals to y minus x, everything squared. You can see that we start at y of 0 equals 0, and we have this time a step size of 0.1. So as always, let's just start right away finding our values based off the initial conditions so that we can start then our steps. So from here, you can see that x naught is just 0, once again, because that's just the value inside of the initial condition. So the initial value will be when x equals to 0. And when x is equal to 0, according to the initial conditions, y is equals to 0, right? So plugging this in coordinates, x naught, y naught, is just 0, 0. So let's use this for our first step. And you can see in this first step, we'll get, once again, that x1 is equals to x naught plus h, which in this case is 0 plus 0.1. So our first x, or x1, is just 0.1. And then our first y, y1, is equals to y0 plus h times our function of x naught and y naught. In this case, our function f of xy, it's the one that we have on top, y minus x, everything squared. So let's replace that one. So we have y naught plus h times y naught minus x naught, all of that square, right? Hopefully this method is a little bit clearer compared to the previous one. And you can see that the function, you can see we're replacing every y and every x in our function for, the corresponding y naught, x naught, and so on, right? So we have to plug in the numbers. So y naught is 0, our step size is 0.1, and then our y naught is again 0, and our x naught is 0. So when you square all of that, it's just 0. So we're gonna find out that our y1 is just equal to 0. So in this case, our step 1, we have x1, y1, which is 0.1, 0. So let's do a second step. So in this one, x2, it's 0.1 plus 0.1, which is equals to 0.2. And then our y2, it's equals to y1 plus h times y1 minus x1 squared. Once again, look at our function, it's changing with the corresponding values. So plugging it in, we get that y1 is 0, h is 0.1, and then in the parentheses, we should have 0 minus 0.1 squared, which now is not going to give us a 0 value, right? So we're going to get a value for y2 to be equals to 0.001. And therefore, in coordinates, this is x2, y2 is equals to 0.2, 0.001. So you can see that for this problem, these problems are pretty easy, right? They don't take too much effort because you're not doing calculus. You're not even doing algebra at this point. You're just basically doing simple additions, multiplications, right? So these problems should be straightforward, pretty easy. If you have these problems in an exam, these should be the ones that you should do first because they don't take maybe more than a minute, right? So it's pretty straightforward, this method. There's nothing complicated, so it's really easy to do. All right, so let's do another step. So in this one, we have step 3, and we have x3 is equals to 0.2 plus 0.1 equals to 0.3. Y3, it's y2 plus h times y2 minus x2, all that square. Substituting the numbers, and you're gonna get then there are y3, it's 0.0049601. So in coordinates, it's the following: 0.3, it's comma 0.0049601. Once again, I'm not truncating any of the numbers just to make things what's it called, a little more accurate, but you guys can of course maybe just not have to try all the like 10 decimals if they're that long. All right, so this is the Euler method. I hope this was helpful. Once again, this is one of the first videos we're going to cover. We're going to do 2 more, the improved Euler method and then the backwards Euler. So hopefully, if you have any more questions regarding this, you can, some of them can be answered in the next video. All right, so that's it on this one. Let's see you on the next one. Until then, good luck.